There we go. Hey there. Alexis. Okay, so then get back over to here. There we go. Now I'm ready. Here we go. Okay, so you guys have been looking at this with your notes and those simulations the past couple days. We're dealing with stuff like called periodic trends. So things that we're looking at in terms of like how can we predict what happens on the periodic table? Okay. This is also going to come important when we get into talking about bonding and why certain things bond with other things. So a couple of the things you need to be aware of are things like effective nuclear charge and electron shielding. So when we are talking in terms of effective nuclear charge, we're talking essentially about how many protons are involved in the system, in the atoms. Okay. Are you leaving me for good?
I have no.
Okay. Well, let me give you your homework for tonight then, before you leave, just in case. There's that. And that. All right, I think I'm losing my mind. Okay. I was thinking he was in this hour, but he must not be. No, I had the wrong hour. Okay. So when we're looking at these things, effective nuclear charge looks at that positive charge, because when we talk about effective nuclear charge, we're talking about the nucleus of the atom. And when we're looking at these extra electrons, we're looking at how much that nucleus can pull on those electrons. When you look at something called electron shielding, then it's these electrons that are inside the valence shell electrons, or the outer electrons, and how much they're going to kind of interact with that nucleus and kind of almost like a sponge soak up some of that pull. So when you were looking at that Coulomb's charge the other day, you saw that there were two things that were affecting these atoms. One of them was distance. So how far these electrons are away from the nucleus. And then the other part was how much force or how much pull you had from here. So force and distance. As the force increased, the pull on that electron increased. As the distance increased, though, the pull on the electron decreased. So we don't do any math with these, but it's just good to kind of understand that relationship. Okay. So our first trend is called ionization energy, and that's how much energy it takes to pull an electron away. The more electrons you pull away from a particular atom, the harder and harder it becomes, because you've got more protons versus electrons there that it's pulling on. Okay. So ionization energy talks about the energy that you're going to need to pull one of those electrons away. And if you go on to take AP, we actually talk about that energy, and we talk about how you can use that energy to determine like what atom, you can use that to identify what atom you're dealing with. Metals tend to want to lose their electrons because remember, and I'm going to personify stuff a lot today, these atoms want to have an electron configuration of a noble gas. That's kind of its ultimate goal in a way, is it wants to look like a noble gas. So if your metals lose electrons, they're going to look like the previous noble gas. And it's pretty easy for them to lose their electrons. All right. So here is your trend. Now you have these periodic tables on your notes. Make sure that you write these arrows in and you write down what they tend to do. And then I'm going to talk to you after you get that done about how this stuff works. All right. So when we're looking at ionization energy, we're looking at pulling these electrons off. So if I have lithium, for example, here, and I pull this one electron away, it's going to have the electron configuration of helium. It's still going to have 3 protons in the center, but it'll have a full valence shell. So it's pretty easy to pull that one electron away from here. Now, to try to pull these guys away, it's going to be much more difficult because at that point, you've got 3 protons, which are really close to these 2 electrons, and they're going to hold them kind of tight. So it's going to be really hard to pull those away at that point. Our potassium here, though, when we try to pull this electron away, that distance is so much greater, even though we still got 19 protons in here, that distance is great enough that it's going to be easier to pull that one electron away compared to this one because the distance is less. And if you remember right, you had the distance affected that pull or that hold, that force more than the charge itself. Okay. So as we look at this, as we move down the periodic table, that distance is increasing. And so because it's increasing, it becomes easier to pull that electron away. Our ionization energy decreases. When we look here going across, our distance is staying about the same if we're in the same period. But when we get over to here, every time we move one element over, we're adding an electron. So we're adding an extra force without the distance changing much. And so because of that, it's getting more difficult to pull those electrons away. Our ionization energy increases. It's going to take more pull to get that electron away from here than it would from here. Okay, and that's what this slide talks about, is going across the period. you back there?
Yeah.
Come here. And all of this stuff up to Miss Jones in the main office. Okay, she'll know what to do with it. All right, so that takes care of ionization energy. Atomic radius, then, we're looking at another trend here, which is called atomic radius. So write this stuff down, and then we'll talk about that. All right. So the first one that we're going to talk about is looking at going down. If you think about it, as we go down, we're adding these electron levels. So it makes sense. It's kind of intuitive that it would increase as you go down. And you can see here with the numbers that this is 0.152. This one is 0.262. So as you go down, you're adding on kind of those layers. Okay. So that's going down. Make sure on your periodic table that's in your notes that you get these recorded. You're going to need this stuff for things that are coming up in the near future here. Okay. Everybody good? Another minute? Are you good? Okay. All right. So going across the thing, though, this is where it becomes a little counterintuitive. So write this stuff down, and then we'll talk about that as we're moving through here. She was there?
Yep, she was there.
Okay, cool. Thank you.
Mm-hmm.
All right, so as we move across, we are adding in more protons. So we're adding in extra things that are pulling in or increasing that charge, but we're not adding any extra layers, okay? So as we move across the periodic table, we're adding in extra charges, which are pulling in those electrons tighter. So it's getting just a little smaller as you move across the periodic table. So that size is going to decrease. Now, as you move across a period, it decreases. But then when you come back down here to the next level, it's going to increase again. Why? This is going to get bigger. It's going to be bigger than this guy over here. Why is we added an extra proton in. Why would he not be smaller? What does it mean when we go down a period here? Why? What have we changed? Yes, exactly. We've added more shells. So here, we've gotten to the end here. We've added more protons in. But now when we move down to here, we're adding another shell in. We're adding another layer in. Okay? So because of that, it's going to get bigger. And then as you move across, you're going to change it from there. Okay? So that higher effective nuclear charge is going to make it smaller until you kick back down into the next row where you're adding another layer in. All right. The third trend that we talk about is something called electronegativity. And electronegativity was created, or not created, I guess, but discovered, named, identified, quantified by a gentleman named Linus Pauling. And he actually did a lot of his work about the same time, I believe, as they were working on the DNA structure, Watson and Crick in biology. So he was working about the same time on this idea of electronegativity. And what he did was he took the periodic table and he made fluorine the base number. We'll talk about why that is when I get onto the next slide. What electronegativity is how much the element attracts an electron. So how badly it wants an electron. And fluorine wants an electron worse than any other element on the periodic table. So write this down, and then I will talk to you about why that is in just a minute. Make sure you get these arrows on here. Again, you're going to need that coming up. This will let me write on here. Yep. Here is our fluorine. Oh, yeah, there we go. Now it's letting me write. So what's weird is that when you think about this, you're like, why is it fluorine and not something else over here? Or why is it fluorine and not helium here? Okay. Well, helium already has a full valence shell. It doesn't need an extra electron. So because of that, it's not going to want an electron that badly. So why is it fluorine and not oxygen, for example, or not lithium? Well, remember, as we move across the periodic table, we are getting to the point here where we have 9 protons that are pulling, and they're like, I want this electron really bad, and trying to get that one extra electron so fluorine can look like neon. Because if it gets one extra electron, it's going to look like neon. Okay? And you're like, okay, well, what about chlorine? Well, chlorine is here, and yeah, it has 17 protons, but the distance here is closer to the nucleus. So you have that draw. And so because of that, fluorine has the highest electronegativity of any element on the periodic table. So fluorine is here. As you move across, it gets less. So for example, oxygen is, you don't need to know this. This is 3.5. This is 3.0. This is 2.5. This is 2.0. And so as you move across, it's getting less and less. Chlorine, I think, is like 3.5. So you can see that it's going to get less as you go down here too, because you're increasing the distance away from the nucleus. So that draw isn't as great. But fluorine is the kind of champion here. Okay. Here is as far as moving, this is across is that we're increasing. And decrease is going down because we're getting more distance away. Oops. Keep moving my thing here. questions about that? Anything there not make sense? All right, then we need to talk about a couple terms here. First thing that we're going to talk about is something called a cation. A cation is an atom that's going to lose an electron. So it has an uneven number of protons and neutrons. Or not neutrons, electrons, sorry. My brain is elsewhere, I guess. Okay, and in this case, it's going to have more protons than electrons because it's lost an electron, or at least one electron. So because of that, it's going to have a positive charge. And so we think of that in terms of, if we write the word cation, if you think of this as a plus sign in the middle here, that helps you remember that that's the one that's positive. And it's positive because it's lost electrons. Anions then are the opposite case. Here, we're going to have more electrons than we're going to have protons. And we're going to have something called an anion. And it's gained electrons. So because it's gained electrons, it has a negative charge. All right. So now we're going to talk about something called ionic radius. When these things become ions, what happens to them? So if lithium gets rid of an electron, it's going to look like helium as far as electrons are concerned. It's going to have 3 positives and only 2 negatives, as opposed to the original lithium that would have had 3 positives and 3 electrons out here. So since it's got 3 positives here, it's going to get smaller. So as we move down, or as we, if we compare this to the original atom, it's going to be smaller. As we move down, though, they are going to get bigger than the one that was preceding it. Why? They've added more shells. Yeah. Okay. So they've added more layers. They're going to get bigger. As we move across, though, these cations are going to get smaller. Do I talk about that on the next slide? Yeah. Okay. So I'll let you write that down and then we'll talk about it. All right, so as we move across here, if we're comparing, for example, a lithium ion to a beryllium ion, okay, beryllium needs to lose 2 electrons so that it can look like helium. If beryllium loses 2 electrons, it's still got 4 positives in here. But now if it's lost 2 electrons, it only has 2 electrons out here. So you've got the charge is so much greater that it's going to pull in those electrons and make this smaller. If we talk in terms of lithium, lithium has 3 protons. If it gets rid of 1 electron, it's going to look like helium. And it's going to pull it in, but it's not going to pull it in as tight as the beryllium. Does that make sense? Because it doesn't have as many positives pulling it in. So that's why as you move across the periodic table, if you're just talking about within the same row, those cations are going to decrease. They're going to get smaller as you move one to the other to the other. Now, let's talk in terms of anions. Do I have another slide for that? Yeah, here it is. So we'll talk in terms of anions next and how they're going to change. So fluorine has 9 protons. And if it gets an extra electron out here, it's going to have 8 electrons here. It's going to have 2 in this shell. That's 10. So here you've got 9 protons pulling on 10 electrons. That's going to be bigger than oxygen. Oxygen has 8 protons. How many more electrons does it need? It's got 6 out here. It needs 8. So it's got to add 2 more. So 8 electrons out here to pull it in to get it to be a noble gas configuration. It's got to add 2 electrons in. So here you've got 8 protons pulling on 10 electrons. It can't pull it in as tight. So that's why fluorine is going to be smaller than oxygen for its anion. Okay. The last thing that we talk about is something called electron affinity. And this is how much energy it takes that happens when they get that extra electron to attach on. Again, get these things marked down on your periodic table because you're going to need those coming up. So this is called electron affinity, and it's going to decrease as you move down. You're increasing that distance. You're also increasing the electron shielding, the electrons that are in that inner, those inner energy orbitals. And so because of that, it's going to take less energy when you remove one of these electrons. And then it's also going to increase as you move across because you're increasing that effective nuclear charge. Okay. Maddie, you want to pass out a couple things for me? All right, and then I just have kind of this is kind of an overview of those trends. So you can kind of look that up if you end up needing it at some point. That'll be on this video as well for you guys.
The concert is next week. Oh, gosh, I know. I don't know if we got to that. Yes. Next week is the one with the ensemble and then the choir. And then after it's off with the homework. Did I give anybody extras?
Are we running out?
Yeah.
I got.
So I feel like there's one special.
I've got these over here. No, I don't. We'll just do the lab.
Hey, Eddie, did you have an extra? Oh, that's one extra. I also have. Look at that. Wait, no. I have an extra. Oh, I got an extra too. Oh.
Okay, here we go.
I think I'm short just one.
The lab or the?
It's the lab.
Okay, so Haman used one of my labs today to make a copy, and I don't think he brought me the original bag.
Okay, I can go make.
So
a copy.
you may have to take this and make a copy of it.
If not, I can take this one. Oh wait, do you want that?
I need to give one to Caleb too. He's at
Oh
home.
yeah, I forgot to use that.
So we've got, if you want to give those out, and then, you got an extra one of these too?
Oh,
Okay,
perfect. Then
there we go.
There's enough.
There's enough of these, and then that's
Yeah.
Caleb's. Okay.
Perfect. Does Caleb need one of the background notes too?
Background notes.
Or the
Yeah, he's gonna need one of those. Do we not have an extra one of those either?
Oh no, we have an extra one of the
Okay.
electrons. Do you want me to go make
Okay.
a copy of this for Caleb?
No, if he needs a copy, otherwise that's his.
Okay.
If we don't need any more, that's his stuff.
Oh, I see.
Okay. All right, so I want to talk about the lab tomorrow and talk about how you guys are going to do that. Let me go over to here. Here we go. Oops, that's not right. Darn it. How do I get that out? There we go. I got to click on that. There. View full screen. There we go. Okay. So tomorrow you're going to have at your lab station, you're going to have a couple of different things. You're going to have a watch glass, which is made out of glass. Okay. You're going to have what's called an evaporating dish, which is a small porcelain dish that's white. You can't see through it like glass. Okay. You will also have one of these water bottles, which I think you're starting to get familiar with those at the table. Remember, if you run out of water, you put it on top of the dishwasher in the back room, and you get one from underneath the table over here if you need more water. All right. You'll also have either a dropper bottle or a bottle with a dropper of something called phenolphthalein. And what phenolphthalein does is if you have a base present, which is also called an alkaline solution, if you have a base present, it's going to turn bright pink. It's kind of a fluorescent, or kind of like Alexis's shirt back there. If you want to kind of know the color, that's pretty much what her color shirt is. So that bright kind of pinkish fuchsia looking color. Okay. So you're going to put a drop of that in here after this is reacted and see if that's turned into a base or not. All right. And that would indicate an alkaline solution. And remember, from labeling your periodic table, the stuff in the first column are your alkali metals. The second column is your alkaline earth metals. So it would not be surprising that they would make an alkaline solution when placed in water. All right. So how do we do this? Do you remember back before COVID when we had buffets? You remember being able to go to buffets?
Oh yeah.
Okay. And you could go to a buffet, and some of the stuff on the buffet, they would carve for you. Okay. They would serve this to you. And then a lot of the other stuff on the buffet was just like free range. You go up and get as much as you want, and you get it out yourself. Okay. Why do you think they did this versus this? Why do you think that they had somebody that they were paying $10, $15 an hour to do this? Why do you think they had that person there versus this situation? Yes, Miss Bella? Exactly. You can't take as much as you want. Now, why would they do that? What's a good reason for that? Exactly. What were they doing? What kind of food was this? This wasn't your bread and your, cheaper stuff. This is the expensive stuff. Okay. Now, the reason why I'm doing this, and it's almost like a buffet line. You come up and you bring me your watch glass, and I give you a little piece of metal on it. Okay. The main reason, and it is expensive, let me tell you. So that's part of it. But the main reason why is I'm trying to control the size that you get. Okay, because if you've ever seen sodium in water, if you've gone on YouTube and watched those videos, and you can, it is quite an experience that these people have. Okay, so I'm trying to throttle how much you get of this. Okay, now this stuff is free range. Okay, typically you take 2 to 3 pieces, but I'm not as concerned about this as I am this stuff. Okay, A, expense, but B, mostly it's a safety thing. Okay, because you can get too much of this stuff. You can get too much of this stuff, so when you put it in the water that you've placed in this evaporating dish, you can actually explode my dish and it'll break. Okay, so that's why I'm trying to control how much you've got. So you're going to put water in this dish, and then you're going to put your metal in there and then cover it with this disc, and then that will you'll watch the reaction. Okay, you're not gonna, are you guys shuffling? Listen to me. You're not gonna touch these metals with your hands. You're gonna use tweezers. Okay, these metals are gonna react to the water. Why would I not have you touch this? What do you have on your skin? In your skin, you have some moisture, right? A little bit this time of year, maybe not as much as during the summer, but your hands are dry, but it's there. Okay, so you're trying to prevent that from reacting with your skin and the moisture on it. Okay, so tomorrow you need to bring in your goggles, you need to bring in this lab sheet and be ready to go. Your homework tonight is 6-3. That is another simulation. You should be familiar with that and be able to work with those. And I'll get that link loaded up on Google Classroom for you. It is in the notes though. So if I don't get it up there, you can go on there and get it. Okay. All right. Let's see here. Caleb, how are you doing, honey?
Good. I got all the notes done.
Okay. All right. Well, let me know if you need anything. Can anybody come by and get stuff for you to work on?
I could ask.
Okay. Why don't you ask somebody, and then you can watch like videos on YouTube of these metals going in the water, if that would work.
And
not be able to
then
do the lab.
fill out the lab report using the videos.
Okay, you guys. Hey, I cannot hear him. Be quiet. Shh. What, honey?
And then would I fill out the lab report using the videos?
Yeah. Yep. If
Okay.
that would work out. Otherwise, if you've got somebody in here that you've got as a lab partner, you could have them call, like, do something on whatever you kids do with, meetings or whatever, and they could do the lab with you tomorrow in class. I know you and Michael will do stuff together. If he has a cell phone, you guys can maybe work something out with that too.
No, my lab partner is Nolan.
Oh, Nolan? Come here. Do you have something where you could work with Caleb tomorrow and show him the reactions on your phone? Can you guys work out tonight? Do you have contact information for each other? Do you want to work out with him real quick, contact information to be able to meet tomorrow on his phone? Or do you just want to use this meeting link? Does that work? Okay, we'll just use this meeting link tomorrow, okay? And you can just watch it on your computer. Is that okay?
Yeah.
All right. All right, we'll see you back here tomorrow then, honey, okay?
Okay.
All right, bye.
Bye.